Welcome! In this video, I'll introduce the iCon hardware and a special Synapse gizmo called Pynapse. The iCon interfaces your TDT system with behavioral cage elements. It connects directly to any RZ processor or the iPac and offers precision control with real-time signal monitoring. The Pynapse gizmo is used to program behavioral experiments. The behavioral logic is scripted in the Python programming language within a friendly code editor built right into the Pynapse gizmo. We will connect behavioral components to the iCon, set up the Synapse rig, and build out whole behavioral experiments in Pynapse. If you don't have physical hardware, you could still do this tutorial. I'll show you later on in Chapter 5 how to emulate the iCon in software. For those with physical hardware, we must first connect the iCon to our processor. If you are running an iPac multi-node controller, connect the iCon to a node port on the back of the iPac. If you are using an RZ processor, connect the iCon to a port labeled DSP-M, SI, or QZ on the back of the RZ processor. Each of these ports connects to a special optical DSP inside the RZ that communicates directly with the iCon. And of course, connect the RZ optics to the interface card in your computer. Newer RZ10X models will have a port labeled M on the front for the iCon. If you purchase the iCon as an addition to an existing system and have not installed the DSP-M card yet, then see the PDF linked in the description below for instructions before continuing on. When everything is connected properly, the iCon status light will be solid green. The iCon is an interface to external behavioral hardware that the subject will interact with. It runs on wall power and has a fiber optic connection back to the RZ processor for communication. It has interchangeable digital and analog modules designed to interface with the different connectors and power requirements of your external hardware. The two most common modules are the IH10 and the IM10. The IH10 connects to 28-volt cage elements from Metassociates and Lafayette. This would include common elements like lever presses, pellet rewards, and nose pokes. The IM10 module handles analog signals, like generating auditory cues or floor shocks, recording microphone inputs, and capturing touch sensor inputs. This tutorial uses the IH10 module. For this tutorial, I have a single nose poke detector with an LED indicator and a pellet dispenser, both connected to an IH10 with Molex connectors. The nose poke sensor input has 3 pins, and the LED output will drive has 2 pins. Each port on the IH10 has buttons for testing the outputs and LEDs for monitoring inputs. When we press the nose poke LED button, we can see the LED light up. When we press the dispenser button, it activates. When we put a pen in the nose poke sensor, you can see the sensor port light up. The LEDs on the bottom row light up when the poke input is true, or when the poke LED or reward buttons are manually pressed. The LEDs on the top row light up when the output is controlled by the RZ from Synapse software. For those of you with physical hardware, make sure everything is connected and powered on. If you are running this tutorial without physical hardware, first launch the Corpus utility on the desktop. Corpus is a full hardware emulator that runs on your PC, and Synapse will interact with it like real hardware. Now launch Synapse from the desktop. And run the rig detect. It takes a few seconds to find all the devices. There we go. It found our iCon and the components match what I physically have connected. If you don't have an iCon or are running Corpus, you can manually add an iCon to the rig for this tutorial. Change one of the DSPs to a DSP-M. Right-click on the DSP to add an iCon, and right-click on the iCon to add the IH10 module. For those using an iPac, the rig will look like this. Exit the rig editor and the iCon is now in the processing tree. Let's configure the inputs and outputs for the iCon. The connectors depicted on this user interface are physically correlated to where they are located on the actual IH10. First, I'll add a nose poke input. We want to name the inputs and outputs something sensible because later on in the Python code, we'll be referencing these by name. We'll turn on the epoch event. This captures the timestamps of when the inputs and outputs turn on and off, synchronized to the start of the recording. We'll also give these epoch events meaningful names. Any data store name in Pynapse is limited to 4 characters, so sometimes the automatically generated name isn't the best choice. We'll call this one Poke. We have 2 outputs, the LED and the pellet dispenser. Again, we'll give them meaningful names and epoch IDs. We're going to control these exclusively from the Python code and not from any other gizmos in our processing tree, so I'll leave this HAL input port option unchecked. For the LEDs, we are going to control when they turn on and off in our code based on the subject behavior. But for the reward, we just want to trigger it once and have it stay on for a fixed amount of time to dispense a pellet. So for that, we'll turn on the triggered pulse option and give it a half-second pulse. Before we go any further, let's save our experiment. Click on the experiment button and select Save As. I'll call it iCon Intro. Let's also add a subject. We'll use the default subject one. Let's run this and see what the user interface looks like. We get the flow plot that will show our event timestamps and a tab for the icon. I'm going to right-click and split the icon tab to the left so that we can see both tabs at the same time. The user interface gives you feedback on what's happening with the I/O that we defined. As I insert a pen into the nose poke device, we can see the LED on the interface light up, and the epoch timestamps are saved. You can see the epoch value is 3 when it turns on and 4 when it turns off. Those values may seem odd, but we'll discuss in the duration testing section later on how you can add additional input logic to capture more information than just the on-off events. You can also manually trigger any of these events by clicking on them. This gives you the same behavior as if you press the hardware button on the front of the physical IH10. Since the outputs are simple on-off events with no other information, just the onset and offset timestamps are saved with the value of 1. You can see this in the flow plot if you click the autoscale button. The LED is a toggle on-off button. Since the reward output is a triggered pulse, clicking this button once turns on the reward output for the 500 milliseconds that we defined earlier. Now that the functional hardware testing is done, it's time to move on to programming some logic. The icon inputs and outputs can link to other gizmos in Pynapse, but primarily the icon is used for behavioral experiments, where logic statements control the experiment flow through different stages. This type of state machine control is very difficult to do in the DSP language of the RZ processors. So we made this gizmo called Pynapse that lets you script your behavioral experiment with the Python programming language and interface with the icon directly in the code. Pynapse integrates your behavioral logic with the state of the hardware. Behind the scenes, Pynapse is constantly checking the RZ for changes to the icon input states, and then it runs any Python functions that we've written to react to those events. These functions are small chunks of code that we typically refer to as slot methods. Calls to these methods are logged and timestamped. Pynapse then sends any scripted changes to the icon outputs or parameters back to the RZ. All of this happens in milliseconds. Often, a specific event will cause 2 very different outcomes in your experiment, depending on what has already happened in the trial. For example, a nose poke at the proper time might trigger a reward, while a nose poke that occurred before the trial begins would cause a failed trial. Pynapse has a built-in state machine to keep track of the experiment flow. It uses the current state name to filter the list of available slot methods that can be triggered. So you code the different slot methods that react to the nose poke and add them to different states defined in your Python code. You also code the conditions needed to advance through the states in your experiment. Using states helps you organize your code and more efficiently record the subject's progress through the trial. We'll see this when we start coding it up. Now click on the RZ and add a Pynapse gizmo to your experiment from the Specialized category. Every gizmo in Pynapse must have an anchor upstream. This is why input number 1 is always enabled on Pynapse even though we won't be using it. So let it link to the reset line on the RZ. Notice 2 things. First, it compiled without error. If there were any issues with the Python installation, we would get an error down here. The latest Pynapse v96 patch includes a version of Python pre-installed that we can use right out of the box. If you want to use your own Python installation, there's a step-by-step guide in the Pynapse manual linked in the description. Second, it automatically attached the icon to itself. This lets us configure all the icon I/O directly in Pynapse and gives us access to the I/O in the Python code editor. If you click on the icon in the processing tree, it will direct you to Pynapse. Okay, so we've added Pynapse and have our icon I/O set up. For now, we'll skip most of the settings in the General tab. The only thing I want to point out is the state epoch. This is the timestamped event that saves in the data tank whenever a state change occurs in the Pynapse state machine. This is enabled by default and we'll leave it on. It's time to start coding. This is the Python code editor, where we will define the logic of our experiment. The code tree on the left shows you all the states and methods in your experiment, organized into blocks of code. By default, the only block of code is main. This is the code that is saved with your experiment file. Whatever is selected in the code tree appears in the editor on the right. By default, there is a single state, the always state. This is a special state that must always be in your experiment and is always active, meaning any method that is defined in the always state can always get triggered, regardless of what state the experiment is in. We'll use this for our first demonstration. You'll see on the right the code structure for defining a state. It includes the keyword class, then the name of the state with a colon, and then a number sign with a state ID definition. The number sign in Python is the start of commented code. It is the equivalent of the % in MATLAB. The comment will get ignored when this code is executed, but this information is used by Pynapse to define a state and give it an ID number. For the always state, the state ID number must be 0. We can see in the code tree that the state ID for always is 0 in the curly braces. Other states will have positive integer IDs. We'll see this later. The colon is used in Python to start an indented block of code. If statements, while loops, for loops, method definitions, and class definitions all use a colon followed by an indent on the next line. Any lines of code that start at that indent level are included in that block of code. This keeps the code organized and readable without being overly verbose. The pass keyword is used as a placeholder for an indented block of code that isn't defined yet. When this code runs, Python is expecting an indented line of code here, so we give it this placeholder by default. It doesn't do anything except make the code valid. Every time we compile our experiment, Pynapse will check if the file is valid and complain loudly if it's not. We can see here if we remove the pass line of code and compile, it throws an error since this is no longer a valid Python file. It's expecting an indented line of code but didn't get one. If you're not familiar with Python, then don't let this scare you. We have templates built into Pynapse so you don't have to remember all this. Let's start with a simple test that requires no state changes. We'll connect a nose poke to the reward. We need to add a method that will trigger when the nose poke occurs. In the code tree, right-click on the always state and select Append Method. This will show you a list of all of the available methods you can add and what events cause them to trigger. They are organized by asset class, so there are system methods related to Synapse mode changes, like idle, preview, etc., and state methods we'll use a bit later. Inputs are Pynapse gizmo inputs. Remember earlier when we added the Pynapse gizmo, it linked input 1 to the reset line. We're going to ignore these. This brings us to the methods we are interested in, the icon input changes. We're not using duration testing yet, so the only methods that can get triggered in our code are the rise and fall methods. We want to trigger the reward when nose poke becomes true, so we'll select the poke rise method. Double-click it to add it to the always state. Pynapse added the stub for this method. The new method is now inside the always state indented block of code. The method definition itself needs an indented block of code. You can see that the code tree can be used for isolating just the parts of code that you want to edit, just the method or just the state, but it's all merged back into one source file under main. I prefer to have main selected in the code tree for simpler experiments so I can see everything at once. Now we need to add some code for it to execute when this event occurs. Notice that any slot method starts with the characters s underscore. Similarly, any Pynapse asset that we want to interact with starts with p underscore. This includes all the icon I/O, state controls, timers, controls, metrics, and more. The Python code editor has very nice code completion, so if you just remember to type p underscore, you can find the asset you're looking for. All the icon I/O is under the p_rig object. You can type the full thing out or highlight it with the arrow key and press tab to autocomplete. The asset objects use dot syntax to drill down into them, so type period to see the list of available outputs. We want to control the reward, so we'll go there. Type a period again to see all the things you can do based on how we configured the reward output. The reward output was a triggered pulse, so we get this fire method that fires the trigger. Just leaving this name won't execute it. We need to complete it using parentheses. Let's also add a print function to write some text to the console when this event occurs. We'll get into the rich logging feature that's built into Pynapse later when we discuss metrics and the session manager, but simple print statements like these can be useful for early debugging. The Python print function will display the string on screen at runtime. In Python, a string can start with a single or double quotation mark or triple quotes if the string takes up more than one line. Okay, what do we have here? We defined a method that captures a nose poke, which triggers a reward and prints something. It's defined inside the always state, so as long as the experiment is running, it's possible to trigger this method with the nose poke input. Now we are ready to test it. Since we have something defined in the always state, we don't need this pass placeholder anymore, so we can clean up our source code a little bit. Let's go back into preview and see if it worked. Here's the Pynapse interface. We have a lot of empty space for now that will fill up later. We can see the current state listed at the top and console output at the bottom. This is where our print statements will show up. I'll fake a few nose pokes and we can see the reward firing along with our print statement. We usually want a more detailed view of what Pynapse is doing. Click this magnifying glass to turn on the debugger. This shows us the call tree and a timeline. The call tree looks very familiar to the code tree that we see during design time. It's showing you all the states in your experiment. We can expand it to see all the methods defined in the state. The call tree is like a mini flow plot. It's a scrolling timeline that monitors when states are entered and when our events occur. This is extremely helpful for debugging later on when events and state changes are happening quickly. You have a history of the whole timeline of how those events played out so you can troubleshoot the logic. For an even more detailed view, click this log button. Like the timeline, this shows you a history of the events. It includes a timestamp of when it occurred and how long Pynapse spent in that function. This green lightning bolt icon tells you the call was successful. A red warning icon indicates failure. You can click on a state or method in the call tree and see the source code for it on the right. You can click a single entry in the call log and see the source code and any console output it printed. Likewise, you can click an event in the timeline to get that same information. We have three ways we can test our single function. The first is by using a pen to physically trigger the nose poke. When I do that, we see the nose poke LED lights up, the poke epoch event fires, and the s_nosepoke_rise function triggered in the timeline and call log. We see the reward LED lit up, the reward epoch fired, and we see our print statement here. Remember, if you see flat lines up here, click the autoscale button. The next way to test our function is to fake the input by clicking the nose poke button on the icon tab. We see all the same behavior, except we didn't have to be physically near the hardware to do this. The third way to test our function is to double-click on the method name. This forces Pynapse to run that method immediately. We see the function ran, the reward fired, and we got some special console output to indicate it was manually triggered and not part of the logic. We don't get the nose poke epoch event, since that didn't actually happen either. Also, this event isn't captured in the call log. Manually triggering function calls is useful for debugging, but once your experiment logic is set up how you like, I recommend disabling this in the General tab. This concludes part 1 of this tutorial. Stick around for part 2, where we will code up an experiment using the Pynapse state machine, metrics, and the session manager. We hope to see you there.